Okay, hey everyone. Welcome to my talk about Vitess at GitHub. My name is Schreiber. I'm a staff engineer at GitHub. I work on the data patterns and scaling team. I joined GitHub 7 years ago, and initially I worked on mostly feature work. So I built the squash and rebase functionality that some of you might know. I worked on the diffs view, on the pull request pages, and on the commit pages. I also worked on the issue timeline, comment view and all the label display and stuff like that. But over the years, I moved closer and closer to database stuff. And nowadays, I'm mostly focused on Vitess work. Now, I've been a Vitess maintainer since last year. So my first an overview of this talk, I'm going to talk about Vitess first, giving a quick introduction for those who might not be familiar with Vitess. I'll give an overview over the over GitHub and the architecture behind GitHub. I'll talk about Vitess at GitHub, how we did the migration to Vitess, and I have some a short overview of the results that we see from migrating to Vitess. And then at the end, we might have some time for questions and answers. So what is Vitess? Vitess is a scalable, distributed, cloud-native database system built around MySQL. It's supposed to be massively scalable and highly available. It's compatible with MySQL 5.7 and 8.0. Vitess is it's a whole bunch of different features all together to make scaling MySQL easier, right? It has support for sharding. It has built-in online schema migrations. It has built-in connection multiplexing, query consolidation, materialization, a bunch of custom management tools, backup and restore functionality, and a whole bunch more than this. Before I go further, I want to explain some Vitess terminology. So in Vitess, there's a thing called a key space, and that's equivalent to a logical database in MySQL, and a key space can either be sharded or unsharded. And unsharded basically means a single shard. A shard is it's like a subset of the data of a key space, and each shard in Vitess is basically its own separate MySQL cluster. And on the MySQL level, that cluster has no idea about any of the other shards in the system. A key space ID is an identifier that is used by Vitess to map a row in any of the tables that you have in a sharded key space to a shard. So each row has a key space ID, and this is only relevant for sharded key spaces. Unsharded key spaces don't have rows, and unsharded key spaces don't have key space IDs. There's a thing in Vitess called a v-index, and that is basically how, a v-index determines how data or how rows are mapped to a key space ID. So, for example, there is a hash v-index that tries to distribute the input values of a specific type to a highly distributed set of output values, so that your data gets distributed evenly across your shards. Each table in a sharded key space requires a v-index, so you cannot have a table without a v-index. But a table can have multiple v-indexes, but they all need to map to the same key space ID. The v-schema in Vitess is basically the configuration for a key space. It holds all the data, v-index configuration, holds a list of all the tables in the key space, all the columns and their types, and also sequence information, which I'll get to in a moment. And it's optional for unsharded key spaces, but required for a sharded key space. And then the last thing is sequences. So because, as I mentioned before, each shard in Vitess is a separate MySQL cluster, that means that each shard is going to generate its own auto-increment IDs, which is a problem if you use auto-increment IDs, because then they'll no longer be unique across your data set. And Vitess has a abstraction built on top, which is called a sequence, and that basically solves this problem and ensures that auto-incremented IDs are actually truly unique across your sharded key space. Okay, so here's a picture that shows a Vitess architecture. On the left-hand side, you have the application servers. They connect through a load balancer to a component of Vitess called dbt gate. Basically, like this is dbt gate acts like a MySQL server to your application. So your application connects to it using the MySQL protocol and sends query to it. dbt gate is the part of Vitess that parses queries, tries to understand what you're trying to, like which data you're trying to fetch, and tries to figure out which shard those queries have to be sent to, and then forwards them to process called vttablet, which is a sidecar to every MySQL instance that you have inside of a shard. The vttablet then executes that query against MySQL and sends the results back to vtgate. Vtgate collects the results and then sends it back to the application server, right? So that's like the high-level architecture of Vitess. Here in yellow, you can see some other components of Vitess. So vtctld, vtorg, and vtadmin, that's like part of the control plane of Vitess. vtctld is like a API server that you can use to manage your Vitess cluster. vtorg is a fork of orchestrator, which some of you might know, but like changed to be specific to Vitess and does failover handling. Like if a node if a primary, for example, in one of the shards fails over, it will automatically elect a new primary from the set of replicas that you have. And vtadmin is a web UI for vtctld. And then we have the topology server. That's basically where all the Vitess configuration is stored. And in most cases, I think that's etcd. There are some other topology implementations that you can use, but I think etcd is like the central implementation. Different components of Vitess can be scaled totally independently. So let's say you have like, I don't know, hundreds of thousands of app processes that connect to your Vitess cluster, then you could scale the VT gate layer independently to make sure that you're not getting overloaded by the amount of connections that come into that layer. If you want to scale reads, you can add more replicas to your shards. If you want to scale writes, you need to reshard your data across more shards, and that will give you more primaries, which can handle a higher write load. Okay, so next, let's talk about GitHub, right? So I'm not talking about GitHub the product, but like GitHub the application. It's a Ruby on Rails-based monolith using MySQL as the main data storage. It's a 14-year-old code base, which you can is noticeable in some areas of the code base, and others is actually like very, very fresh. We are running a bleeding edge Rails version, so we are always running on the latest nightly builds. We have our own Ruby architecture team that works on Rails features that are important to us. The monolith connects to more than 20 database clusters, and we run over 100 application processes, and they all connect to these database clusters. So there's like an enormous connection count coming into the database clusters. We try to follow Rails best practices, right? So we have, like all of the tables that we have use auto-increment ID columns. We do not use any foreign keys in the database, and we manage schema changes via Rails migrations and some integration with a tool called Ghost, which some of you might be familiar with, which is an online schema tool that was built at GitHub. So we have a fairly standard MySQL setup at GitHub. So we run around 80 MySQL clusters, all in a primary replica setup. And we try to offload as many requests to replicas as possible and only have like the write load go to primaries. In total, we run over 1,200 MySQL instances that run on bare metal hardware. We have another set of 300 non-production instances running on Azure in VMs. And we have a mix of feature-specific clusters that only hold data for specific features. And we have also shared clusters. This is like mostly the older clusters that we have had like for 10 plus years, where we have tables that are used by many different features. At peak, we have 5 million queries per second across all these MySQL replicas that we run, and around like 500,000 queries per second on the primaries. Like the total amount of data that we store on the primaries is around 330 terabytes of data, and that then gets obviously replicated out to all the replicas that we run. So when we needed to scale MySQL, we basically employed 4 different strategies. So when we build new features, we try to build them using completely new clusters to make sure that there's like no overloading or unexpected growth happening on existing clusters. We would also break up existing clusters if they became unbearable to manage. For example, a few years ago, we have like our main database cluster is called MySQL 1, and it stored both user data, repository data, issues and pull requests, like everything, like most of the data that we had was stored there. And we had like a big project where we basically carved out all the tables that are related to repositories and issues out of this cluster to make to ensure we could like scale our system. Another approach that we have is adding more replicas, right? Like if we need to scale the read load, we just like add more replicas to the cluster and done with that. If we had to scale for higher write load, our approach was mostly to just use bigger hardware, right? Like just bigger machines, they'll handle that, right? Eventually, like that approach that we had before didn't really scale as far as we needed that to scale. Like we started hitting limits. So hardware upgrades are getting more and more expensive the better the hardware is that you need, right? And we like to scale write load, you cannot just like go and upgrade your primaries. You have to upgrade the whole cluster because you want to make sure that if there's like a failover happening, you don't fail over to burst hardware and suddenly you have like a huge outage because you're using like a machine that cannot even handle the load anymore. We also had problems with the schema migration times. So we had cases where like just adding a column to an existing table could take like months to do. And this is like really, really terrible for application developers because when they plan working on a feature, they don't often think about these things. And then like that feature gets delayed for months because they need to wait for a database migration. We also had problems with the buffer pool. So what happens frequently is that the frequently used data set was much, much bigger than the available memory on the hosts, right? And what happens then is that MySQL is constantly paging data from disk into memory and then throwing that out again because it now needs like suddenly it needs to access other data again. And like you have like this constant paging in and paging out of data into memory from disk. And then we also had problems with replication lag. So we had some clusters where the replication traffic itself was so massive that the replicas could barely keep up with that traffic and serving read traffic at the same time. So obviously you can add more replicas, but those replicas are also getting bound up with replication traffic. And adding more replicas to a cluster had basically almost no noticeable impact on the read load that you can handle because like, all the replicas are already busy just with replication traffic. So when we looked into different solutions for these problems, we eventually decided to use Vitess to solve them. So why would we use Vitess, right? For us, I think the biggest reason is that Vitess is still MySQL at its core. Like we made a lot of investments into MySQL, like we have a lot of automation and tooling built around MySQL. Application engineers are very familiar with developing features for MySQL. Existing application logic is built with MySQL in mind, right? So I would say we know how to run MySQL in a good way, and switching to a different platform comes with a lot of like known and unknown risks, right? You don't know what will break with a different solution. So staying with MySQL is like very interesting for us, right? The other reason why Vitess is a good fit for us is that Vitess's sharding model, like sharding tables by a sharding key, fits our data model extremely well in many cases. So if you think about GitHub, right, most of the data is grouped by repository. So sharding by repository ID, and like we have like millions of repositories, right, makes a lot of sense. It distributes the data very evenly across the shards. Most of the queries don't go across shards, so like it's a very good solution for us. And the third reason is acceptable query compatibility. So Vitess tries to be fully compatible with MySQL. That's not always true, and we're going to get into cases later where that wasn't true. But overall, I think that's like a big goal of Vitess, and that makes it easier for us. Like one big thing for us is like we have a product called GHES, which is an on-premise solution for GitHub, which customers can easily buy and set up on their own virtual machines. And that solution runs with MySQL. So if we run Vitess in production, we still want like full MySQL compatibility, and we don't want to build features just for Vitess, because they still need to run on GJS, and we don't want to run Vitess on GJS. Okay, so a timeline, right? In 2018, 2019, we ran our first experiments using Vitess. In 2020, we actually moved our first cluster over to Vitess. That was all the notifications data basically moved over to Vitess. This was using Vitess 7.0, and we run this in a 4-shard cluster. And since we migrated the data over to Vitess, it has stayed in this 4-shard cluster. So we didn't do any resharding. Same for webhooks data, that also moved in a year later in 2021. Same kind of setup, 4 shards, has been running on those 4 shards since then. In early 2022, we moved actions, checks, and statuses data over to Vitess. I was using Vitess version 13. We initially moved that into a 2-shard cluster, very quickly resharded to 4 shards, and are now thinking about resharding again to 6 or 8 shards. This cluster had like 30 terabytes of data at migration time, and today it's like over 100 terabytes of data. So we have seen like enormous growth in actions usage. Each shard is 25 terabytes. Yeah. Yeah, I'll get to that later, okay? In early 2023, we also moved the issues and pull request data to Vitess using Vitess version 14, and we immediately set this up as a 16-shard cluster because we didn't want to run into the same problem as with the actions and checks cluster, where like these shards become masses. Right. Okay. And today we run 20 key spaces on Vitess. Out of the 330 terabytes of data that we have on MySQL, 150 terabytes is actually stored in Vitess. And we see around 750,000 queries per second peak across all the Vitess key spaces that we have. This includes both replica and primary queries. Okay, but like, how did we actually do this migration to Vitess? So migrating to Vitess was a multi-step process. And like roughly it consisted of these like 6 steps here. So we prepared the existing schema for sharding support, the validated correctness via CI. We performed query analysis to make sure like we don't have any regressions in performance. We copy and sync the existing data in a new cluster, validated performance in production, and then did the final cutover to Vitess. Some of these steps can actually happen in parallel, but just like for ease of understanding, I'll just go through them one by one. So the very first thing we had to do was figure out how we will shard the data. And as I mentioned before, sharding by repository ID makes a lot of sense for us. But in the existing schema, not all tables had a repository ID column. So the first thing we had to do is figure out which tables we want to move to a sharded cluster, and then add a repository ID column to all of them, and backfill this column with actual data. So in like Rails terms, it looks something like this. Like for every table we want to migrate, we had to prepare a database migration, add the new column, run this on production. And then we would change the model code to make sure that like all the new records get created with a repository ID. In this case, like all the pull request reviews would get created with a repository ID taken from the parent pull request. And then we would do something like this, where we loop through all the data that we have in the database and run like this SQL query to fetch the parent repository ID and write it to the record. Obviously, this is like very simplified. We have a lot of logic to throttle queries and make sure we don't overload the production system when we run things like this. And then we had to repeat like this process for all the tables that we wanted to move. So for actions and checks, for example, this was like for 8 tables. Issues and pull requests was like more than 50 tables, out of which I think 40 or something like that needed that data to be backfilled. And it was like this process was the main time sink required for migrating to Vitess. I think it took like half a year to actually like just backfill all this data in a way that doesn't impact production. Once we did that, we could focus on validating the correctness. Like we wanted to make sure that all the queries we run on MySQL today will behave the same way when we run them against Vitess. So we needed to figure out how to run Vitess in local environments in CI. We needed to find a topology for Vitess, define a v-schema to be used, and then we would basically go try run our tests, figure out what fails, and fix those failures, right? So for running Vitess locally, we decided on using vtcombo. vtcombo is like a single binary that you execute and put in front of an existing, like a single MySQL instance, and it will act like a full-blown Vitess cluster with many key spaces and shards and all this stuff, but only requires a single MySQL instance. So it makes like the whole Vitess setup much, much simpler and is like perfect for running things locally or in CI. Then next we had to define the topology. Here's like an example topology configuration used by vtcombo. It's a protobuf text file, looks a bit like JSON, but it's not exactly the same. In this example, like we have one key space called GitHub development VT, which has only one shard, so it's like an unsharded key space. And then we have two more key spaces, one for issues and pull requests and one for actions and checks, which are both sharded. And for us, it's enough to have two shards. Like we don't need 16 shards or whatever in development because it makes everything much more complicated. And like Vitess needs to just like run more internal processes. It's enough to have two shards because if you can validate that your query is performing correctly in two shards, it will also perform correctly with 3 shards or 4 shards. And then we also worked on defining a v-schema. Initially, this v-schema was defined fully manually, but we built like some automation that hooks into Rails migration framework to auto-generate these files. So here, like this excerpt here shows the v-index configuration, and I made a mistake. There's like a comma there where one shouldn't be. But like we define a hash v-index, and this is like a lookup v-index. Those lookup v-indexes, like I won't go into a lot of detail there, but they're important if you have queries that don't include the sharding key. Like we have a lot of queries because of the way Rails works, where we do lookups only, for example, by issue ID. And the lookup index makes sure that those queries perform well as well as those that explicitly contain a repository ID. And then here, we also have like the table configuration of a v-schema, where we have an auto-increment setting, which points to the sequence to be used for the ID column. We have the column v-indexes. So here you can see we use the hash v-index for the repository ID, and we use the issues ID lookup v-index for the ID column. Then we have a list of all the columns and their types. And this is important because Vitess needs to give like a consistent view to the application of what the database schema looks like. But different shards can be in different states, right? Like let's say you run an online schema migration. One shard might have already applied the schema migration and might have different columns than all the other shards. But Vitess needs to like give a consolidated view of what the actual schema is going to be to the application. And that's why it requires specifying the database columns and their types in the v-schema. And basically at this point, we were ready to run Vitess using RCI, and what could possibly go wrong, right? We made all the setups that we required, and when we actually ran this, everything fell over, like nothing worked at all. And this was great. So we needed to figure out what was going on, right? And when we did that and we looked through the output log of our build system, we quickly understood that like there's a lot of very, very similar failures. And we needed to first focus on like the most impactful failures and then like figure out what else was broken later. And the number one problem that we saw was that Vitess didn't have any support for save points at all. And this is a problem if you use Rails, because Rails uses save points to isolate unit tests from each other, right? So it creates your database and sets it up at the beginning of the test run. And then each test case is basically wrapped in like all the test runs are wrapped in a big transaction. and each individual test case is actually wrapped into a save point. And at the end of the test case, the save point is rolled back, right? So that basically isolates database changes. And that support was completely missing from Vitess. So that caused everything to fall over. Big shout out to Harshit from the Vitess maintainer team, who very quickly implemented a pull request that added save point support to Vitess. But there was like a whole bunch of other issues that we ran into, which I'm not going to like go into detail here, but you can look, like download these slides later and then look at all the references I put in. There was like a whole bunch of features or like things that were wrong in Vitess that caused queries to return different results in MySQL, which is a bit scary, but like, again, that's what we wanted to do. Like we wanted to make sure that things actually behave the same way, and that helped us, like running CI against Vitess helped us to understand what is currently broken in Vitess. And once we were done with this work and everything was green, we were sure that like Vitess is going to work the same way as MySQL. And we're like continuously running all the tests that we have. We have like a build that uses MySQL, and we have a build that uses Vitess going forward. Like we make sure that nothing ever changes. And if someone like introduces a new functionality that uses something in Vitess that actually works differently in MySQL or the other way around, we'll have a test failure, and then we can figure out what's broken, if something is broken in Vitess or maybe in MySQL, right? We don't know. But we will get notified automatically. Okay, so the next step for us was to perform query analysis, right? And the reason here is even though queries might return the same result between Vitess and MySQL, we didn't know whether queries would actually perform the same way between Vitess and MySQL. And testing performance using unit tests is not a great, like you cannot actually like verify anything there, right? So what we did is we got a sample of every query type we run in production. Like we got multiple samples, and then we ran them through a tool called VT-explain to get information about how Vitess is going to actually like handle this query. And what we found is like we wanted to understand when and why Vitess is rewriting it or like splitting a query into multiple pieces. And this can happen like if you have a cross-shard query, like where data, you're trying to like load data from different repositories, that will go to different shards, right? And in some cases that is totally fine, because that's the only way to implement a specific feature. Like let's say a user wants to list all the issues that they have created across all the repositories. That is a cross-shard query. You cannot solve this by just going to one shard. So in those cases, like these cross-shard queries are fine. But if like the optimal case for a query is usually if Vitess takes the query, just sends it to MySQL, gets the result back, and sends it back to the application without doing like any cross-shard query planning or like special query execution or query rewriting. Like if it doesn't touch the query, that's the best case, right? And we wanted to understand when that is not going to happen, like when Vitess does something weird. So we wrote a tool to do this and to create automatic issues in our repo, and that created 600 issues, right? Like this was not great either. So we had to figure out what is going on here. And similar to the unit test failures, we went through those issues and tried to group them by similarity. And again, we saw many similar themes where like a single thing in Vitess that didn't work quite the way one would expect to would cause like a whole set of queries to behave differently. And our approach was to like, where possible, fix those issues in Vitess. Because again, Vitess's goal is to be compatible with MySQL. And that also means be like have the most like the best performance for queries where there's like no sharding involved or like no like real reason to do like cross-shard queries. And we only fell back to changing application logic if there was no clear fix for something in Vitess. One thing that I worked a lot on was subquery handling. There was a bunch of subqueries where Vitess had trouble planning the queries correctly, and it would end up breaking up queries into like multiple pieces. And in some cases, like those broken up queries were really, really terrible. Like it would try to load a billion row table into memory on the VT-gate layer, like all the data, and then try to like do a nested loop join there. And that just didn't work, right? So I worked on fixing this, and I worked together with Andres Taylor from the Vitess team, who like did a lot of pairing with me on fixing like planner issues like this. And there's like, again, a whole list of other issues that we encountered where things were not optimal that we worked on fixing. Eventually, we fixed most unexpected scatter queries in Vitess, or like by using by improving the query planner in Vitess. And there was only a handful of query fixes that we had to do in the application. Like my favorite example is we have something called cross references, where you can have issues reference other issues in other repos, right? And those are going to be cross-shard queries because you load data from different repos, right? And we had one case where a very more or less basic query was turned into 16,000 queries by Vitess. And it had like terrible performance. And there was no way to fix this in Vitess properly because Vitess doesn't know, like Vitess doesn't have access to MySQL statistics. So it doesn't know what the perfect join order is going to be. So what we did is just rewrite the query in the app, split it into two, and then that would only run like 17 queries in Vitess in the end. One query per shard, plus the other one query at the beginning. Right. Okay, so the next step then, once we were sure that like query performance was fine, was to copy and sync existing data from the existing cluster over into the new 16-shard cluster in Vitess. And the way we did this is actually just like put Vitess in front of the existing cluster, set up the new shards, and then use a Vitess command called move tables to copy the data from the old cluster into the new one. And the way move tables works is we'll like read the bin log from MySQL and continuously copy data to your new cluster. So it's basically like the two clusters are going to be in sync all the time. And then you can do like performance testing or like run queries on the new cluster. And that's what we did to validate performance in production. We have a Ruby library called Scientist. I don't know if anyone heard about that before. The way Scientist works is you can take two code pieces, run them one after the other, and then compare performance. And you can like designate one piece of code as being like the correct one, and this is the one that is always being returned. And the other one is run just to like collect metrics and make sure that the results are the same. And what we saw was that like query performance in general was comparable between Vitess and MySQL. It was a bit worse than MySQL because Vitess has more components that queries need to be passed through, but this was like something that we expected. And we also saw a low number of mismatches between the results, but that is also kind of expected because those two queries run on different clusters and data can change in between those two queries. Like there's no transaction guarantees there, right? But we looked through the mismatches that we saw and they were like super low, and it was pretty obvious that those mismatches mostly happened because of data changes in between executions. Eventually, we built a feature flag to allow redirect and read queries to Vitess, and we enabled that feature flag to all project members that worked on the Vitess migration. And we were actually surprised how well things worked from the get-go, because we did all this like analysis stuff up front. I don't think we actually encountered a lot of issues once we enabled this. And we very quickly also rolled out that feature flag to all employees at GitHub to make sure that like we actually like have some load going to Vitess and make sure that everything works fine. Eventually, we started doing, or like we planned for the cutover to Vitess, and that was done by moving all the existing read and write queries to go through the VT gate layer, but still go to the existing cluster. And then Vitess provides tools to basically switch read and write traffic at the VT gate layer in an atomic fashion, right? So you can like switch all the traffic over to your new cluster. You can, in theory, you can also switch it back, and Vitess will like handle all the details around this. And switching traffic, like switching write traffic, basically only causes like a few second blip where the application cannot write to the database, and then everything just continues working again. And we were finally successful with the cutover on the third attempt in both the actions and checks migration and the issues and pull request migration. I think only one of those attempts were because we encountered a bug in Vitess where we had to roll back the change. All the other problems that we had during the migration were basically like caused by something weird in our setup. Okay, so let's talk about the results of this migration, right? So the old cluster in the issues and pull request case, the old cluster had one primary and 100 replicas just to serve the read load. And those are not tiny machines. They're massive. They have I think 64 CPU cores, 768 gigabytes of memory. So that cluster was really, really big, and it was already running on its limits, right? And the new cluster that we set up for Vitess, where we moved the tables to, had 16 primaries and 84 replicas only. And we had less machines in the new cluster, and those machines were also less potent, right? They only have 265 gigabytes of memory. So there's a huge difference in cost between those two setups. What we also noticed is, I mentioned this before, right? Online schema change duration times were really, really bad before. So on the largest table in the issues and pull request cluster, I looked up the time it has taken us to add the repository ID column. On the largest table, it was 3 weeks. On the new cluster, after the migration, we ran a database database schema change that took 2 days, and it had no impact on production. Whereas before, we saw constantly Ghost has a throttling mechanism, and during the weekdays, Ghost would constantly throttle, and only on the weekends we would actually progress with the schema change. And on the new cluster, it just ran through, and there was no impact on replication lag or anything like that. I think you can see here pretty clearly when we did the migration. So this is the read rate from disk across the primary on the old cluster and across all of the primaries on the new cluster. So this at the bottom is a sum of all the primary data read rates. And what you can see here at the top is that on the old cluster, we were peaking at over 160 megabytes per second being read from disk. And on the new cluster, I think this is 24 megabytes per second across all the primaries that we have. So what this means is we're making much, much better use of the memory that our clusters have, right? We don't constantly load data into memory and then load some other data into memory again, because we just, the working data set is most likely held in memory all the time. What you can see here is the QPS on the old cluster and the new cluster. And this is quite interesting. You can see that the QPS only dropped by around 20,000 QPS when we moved the issues and pull request data. But you can see the QPS increase on the Vitess cluster is more like 80,000. And where is this coming from? The reason for that is that we that we still run a lot of cross-chart queries. And if you have a cross-chart query, that gets multiplied by 16 times, right? You need to run this query on all 16 charts. So instead of running one query, you run 16. But that happens in parallel, so it's not that bad. And on top of that, we also have these lookup v-indexes that I talked about before. And each time you use a lookup v-index, that actually involves a second, two queries to the database, the lookup v-index query, and then the original query that you actually want to execute via Vitess. So that's where the higher QPS comes from. But at the same time, we also have many more primaries, right? So each primary actually only sees less than 10,000 QPS. Whereas the old primary before was already sitting at 80,000, right? And then here we also have the read rate across replicas, which is also super interesting. You can see here that we were peaking at 16 gigabytes per second. All the replicas were reading 16 gigabytes per second from disk. And the new replicas in the new cluster are sitting at less than 1 gigabyte per second being read from disk, right? So that's a huge, huge improvement. And we can actually see this in the performance. Overall performance is roughly the same, right? It's a wash. Some queries are slower, especially fast queries are slower than before, but slow queries are faster than before. And the reason for that is what I mentioned before, is that Vitess has an overhead. You send a query to Vitess needs to parse the query at the VT gate layer, figure out how to actually, where to forward that query. Then it will forward it to the VT tablet, where the query is parsed again. The VT tablet will forward it to MySQL, where the query is parsed again. So you have more and more steps in between. So if you had a query that would execute in less than 1 millisecond, that might now actually execute in 2 milliseconds from the application point of view. But at the same time, slow queries are much, much faster because the data is more likely to be in memory already. And we had like cases where queries were like constantly run at like 120 milliseconds on the old cluster. And like every time you reloaded the page, it would be like 120 milliseconds again because you might have hit a different replica out of the cluster. And in Vitess, those queries are now running at like a constant 30 milliseconds or something like that because the data is already in memory and not being constantly loaded from disk. So a big thank you to all the colleagues at GitHub that worked or like helped to make this migration possible. And also a big thank you to all the Vitess maintainers that helped us to resolve the issues in Vitess. So I think we have a few more minutes for questions. I think, yeah, like there was one question during the talk regarding TiDB or some other like cockroach or something like that. So from my understanding, like what is important for us or like for the performance of our application is that for a lot of the queries that we run, I mentioned this before, they're scoped by repository ID, right? So it makes sense to co-locate data together that belongs to a single repository on this, like on the same MySQL instance. So that when we run queries that have joins or something like that, there's like no network access involved, right? You just send it to MySQL executes the query, results come back. If I understand correctly, like TiDB always distributes all your data across all the nodes that you have. So if you have queries that involve joins across different tables or like require loading a lot of rows, that means there's like a big fan out across your whole fleet, which makes performance worse than if data is co-located. So that's like one of the reasons why like TiDB, I think we had like a proof of concept or something like that for TiDB, but eventually we used Vitess. One, yes. Each host only runs one MySQL instance. There's like no shared architecture or anything. So we manage the hosts themselves are managed using Puppet, and then Vitess deployments we manage them through a system that we call Heaven. It's like a deployment system that was built at GitHub. And like when we deploy a new version of Vitess, what we do is we basically restart all the replicas to use the new Vitess version, and then we do a primary failover, and then restart the old primary Vitess components. VTGate is actually running in Kubernetes, so it's like a very easy deployment. But like VT-Tablet is a bit more involved because you have to do this like primary failover thing. Yeah. Okay, so shard migrations, like Vitess has tooling to do resharding. So basically the way it works is you build up new shards, then you run reshard, which copies the data from the existing shards to the new shards, and then you do like a switch traffic again. So Vitess handles all the resharding for you. It's a bit expensive because you basically like need to build a new cluster with all the machines that you have, or like you need like twice the amount of machines, and then once you're done with the migration, you throw away the old machines. I think newer Vitess versions support something called sub-shard resharding or something like that, where you can only where you can say, okay, I'm only going to reshard this one shard that I have here into two shards, and then I'm going to take this machine and add only one additional machine and then like do another like split of a shard, right? So you can do partial resharding. So you don't need to like build a complete new cluster with all the machines that you need for all the shards, but you can do it step by step. We haven't used it yet. I don't know how well that works. The other question was, whether we want to move everything to Vitess. I don't think so. I don't think that's currently the plan. We have been talking about this every now and then. So far, we haven't decided, and I think like there is an overhead to running Vitess, both from application performance point of view, right, as I mentioned before, and also from a management perspective. Like you need people to actually manage your Vitess clusters. And so far, we've only done this for when we actually needed that, and for the clusters that only run MySQL and are fine just running MySQL because they don't have like an enormous growth rate. There's no pressure to actually move over to Vitess. So Vitess has a tool that is called VDiff. I think the newer, like there's VDiff 2 now, which can actually do that. And VDiff2 is also a lot faster, so it's much easier to run it again. I remember during the actions and checks migration, we ran VDiff, and it took like a month to, or like not really a month, but we ran into all sorts of issues, and we had to restart it over and over again. For the issues and pull request migration, we used VDiff2, which was much, much quicker. And yeah, I understand the point that like, how do you verify that the data is staying consistent over time if you don't rerun VDiff? But I mean, like the way vReplication works is based on the MySQL replication log, and it's all like transactionally safe, the way it works. So I guess at some point you have to trust the system to work correctly. But I understand the point, yeah. But I think VDiff2 makes things much better. So you can resume verification, and it's also not as expensive as before to just like start from scratch. Yeah, I guess so. But like, yeah, I mean, like, yeah, you cannot, like, Vitess has fail-safes around the cutover, so you cannot cut over the traffic unless all the data has been replicated over. And yes, if there's a total bug in VDiff where data is being lost, that would be bad. But I think like the Vitess maintainers are putting a lot of thought into changes that they do to vReplication to make sure that this doesn't happen. Yeah, it has rollback. And I think it had rollback for a long time. I don't know when that was added, but like since I started working with Vitess, it had the rollback functionality. We had those few cutover attempts where things didn't go correctly, and I think we only needed to roll back once. Like we had a few attempts where we never actually got to the point where we switched all the traffic over, and we had one attempt where we switched traffic over and had to switch back, and that worked flawlessly. So like we had a pretty good experience with the Vitess tooling in that kind of regard. So, any more questions? Yeah. So for a long time, we haven't upgraded Vitess if we didn't need to. So every time we moved to a new, we tried to move a new cluster with like new functionality or new query types, we encountered issues, and then eventually we had to upgrade Vitess because, like, again, as I mentioned, all these bug fixes that had to happen before we could move over. I'm currently working on making Vitess upgrades a more like regular thing that we do. So yeah, it's like it has been something that we haven't done a lot. I want us to do it more often to make us like more comfortable doing it. Because the longer we wait, the more changes pile up in Vitess, and then it becomes like really scary to do an upgrade because you have no idea what is going to break. But yeah, so far, again, we haven't done it often, but we've done it every now and then, like maybe once or twice per year. I want to do that much more often in the future. Yes, foreign keys break. Yeah, Shlomi's blog post. There's like one blog post by Shlomi who worked for a time at GitHub, and basically like foreign keys break all online schema migration tools. So if you're fine having downtime to run database alter statements, it's okay. It might work, but we are absolutely not fine to like take down the system for like 3 weeks to run like a table change. So Yes, they cause a lot of problems. I know that I think PlanetScale is working on adding foreign key support to Vitess. The way it works is that it completely ignores foreign keys in MySQL and re-implements foreign keys logic in Vitess. So that might be something that is interesting to you if you require foreign key support. And that basically, I think, helps to completely like sidestep all the issues with foreign keys. And online schema migrations, but we are not using them. I don't think we'll ever migrate to use them, so they're not relevant to us. We use joins, yes. Like we don't use like the foreign key thing that is built into MySQL, but we use joins and all the stuff, yes. Sorry? Yes, yeah, like not the explicit version. Yes, they run on the same host. I mean, you can run them separately, but then it's like another network hop that you have to do, and I don't think it makes sense. If you want network traffic to be encrypted, yes. What do you mean by size? Like number of processes? I don't think we put in any limits. Like it just runs on the same host side by side with MySQL. I don't think we don't run a container system. Yeah. No, like MySQL probably uses like, I don't know, 90%, I guess, something like that of the memory that you have. Yeah. Like compared to like the 700 something gigabytes of RAM that MySQL uses, it's like nothing. I think like 6% or something. No, 6 cores maybe at peak or something like that. Like it's not a lot. Yeah, I can look at the graphs. I'm not going to open them here, but if you're interested, you can. I mean, we're fine sharing a lot of details, but no, we run everything with InnoDB. So I don't think the Vitess supports anything except InnoDB. Does MyESAM have GTID support? Right, but like a lot of other features, I think, depend on InnoDB transactional guarantees. Like you cannot do replication without transactions. Like how is that going to work? Like yeah, okay, yeah. If you have more questions, feel free to find me. I'm happy to answer them. There's no plan right now.